In this lecture, we will be looking at the inverse transform method. The inverse transform method is a type of sampling method. So suppose that you have a random variable u that is uniformly distributed on the interval 0, 1. Remember, that intuitively means that if you think about drawing a random number from the interval 0, 1, you get anything in here with equal probability. That isn't mathematically the correct way to say it, but that's the way to think of it. And its cumulative distribution function is given here. So its CDF is equal to, if we have on this axis here u, and we're going to graph its CDF, or its cumulative distribution function, say in blue. If u is less than 0, then the CDF is equal to 0. Then if u is between 0 and 1, it's equal to u. So it's going to be this 45-degree line on that interval 0, 1. And then we hit 1 if u is bigger than 1. We want to take a random variable that's uniform 0, 1 and use it to generate a different random variable. And there are many reasons why we might want to do this, but the underlying principle is that a uniform 0, 1 random variable is about as simple as a random variable gets, a non-trivial random variable. And we can actually, in a relatively straightforward way, generate pseudo-random samples of these types of uniforms. And a lot of what people call random number generation, which really should be called pseudo-random number generation, is based on the idea of having the ability to generate pseudo-random uniform 0, 1s. And we say pseudo-random because when you're generating random variables on a machine, you are actually generating things deterministically, but you're generating them in such a way that they look random. And by look random, we mean they can fool some type of high confidence hypothesis test, that they actually are coming from your uniform 0, 1 distribution. And these are used in many different applications. Probably the most important example is in Monte Carlo methods, where you're sampling random variables many times, usually in the millions. And oftentimes when you're doing that, the driving term underneath is a uniform 0, 1. They also come up in risk measures when we are looking at how to measure risk for a portfolio loss. And they also come up in copulas. So when we use copulas to model dependence amongst different random variables, the inverse transform method is really fundamental in there. So these are just 3 examples of contexts in which the inverse transform method is particularly important. And let's see how we do that. So again, it's a sampling method. We're going to use a uniform to get a random variable from a different distribution. So suppose that we're after a random variable, say x, coming from a distribution with cumulative distribution function f. And let's assume that we are in the nice case where the CDF is strictly increasing and continuous. So the uniform 0, 1 random variable, that takes values in 0, 1. So we can think of it like a probability, but we can think about it like a randomly selected probability. Now, because our CDF-F is strictly increasing and continuous, it's a nice CDF, it has an inverse. So it has the inverse function, we'll call it F inverse. And note that a CDF has a range of 0, 1. right? A CDF gives you probabilities. The CDF F being strictly increasing and continuous means it should look something like this. Now, of course, that means its range is the interval 0, 1. Thus, its inverse has domain 0, 1. A function and its inverse swap domains and ranges. So if F inverse has domain 0, 1, well, U, our random probability, comes from there. So what happens if we pass this U, this random probability, to the inverse function of F? Let's try it and see what happens. We pass U to F inverse and just call it Y. And let's see how that turns out. What's the distribution of this Y? And it makes sense. Y is a random variable because U is a random variable, and then we're passing it to a deterministic function, so that should end up being a random variable. So let's look at its cumulative distribution function. So the cumulative distribution function of Y, by definition, is the probability that Y is less than or equal to some fixed value X. Well, we said Y was F inverse of U, so let's just replace Y with F inverse of U in here. But then recall that we can take F of both sides here because we have the inverse of F inverse, or F itself. So if we take F of both sides inside this probability here on the right, F of F inverse of U will just leave us with U. And over here, X will become F of X. And we can do this because F is a strictly increasing function. So when we make that change, we now have the probability that U is less than or equal to F of X. But let's think about that. So U, again, a uniform, F of X, well, little x is fixed. F of X is the CDF, F evaluated at X. So this F of X is just some number between 0 and 1. So this is saying we have this number, F of X here, it's some number between 0 and 1. Well, what's the probability that a uniform 0, 1 random variable is less than or equal to F of X? Well, that's nothing more than the length of this interval here, 0 to F of X. So the length of this interval is the probability that that uniform lands in this interval. So the length of 0 to F of X. Well, what was the length of this? Do your right endpoint minus your left endpoint. F of X minus 0. It's F of X. So the length of that interval is just F of X itself. Well, if the probability that Y, our new random variable, is less than or equal to value X is equal to F of X, that means by definition, this F is the cumulative distribution function of Y. So Y has that distribution that we wanted. Y is a new random variable with CDF F. And the idea is that we have used a uniform random variable to generate a more complicated random variable by using its CDF kind of like a filter. So we can also imagine it graphically in the following way. So we know that our CDF, whatever it looks like, it's strictly increasing and continuous. And usually when you think of your CDF, you think of picking an X value down here, and then you go up to your CDF, and this value here is the probability that your random variable is less than or equal to your value on the horizontal axis. But we can think of this now going the other way. So we are selecting a random probability which we're calling u. That's our uniform 0, 1. We then go through the distribution function in reverse, in other words, going through its inverse, and that is then spitting out what we called y. And y has the distribution specified by this CDF f. So we can think of it like a filter. Again, we generate a random probability, some random number in between 0 and 1 here, uniform. Then we send it over through the inverse of the CDF, and that spits out this y. And because we filtered it through the inverse of that CDF, y has the distribution that we want. So when you have a distribution function, a cumulative distribution function that you can invert, you have this very nice method where you can use these uniform 0, 1s to generate random variables that have the distribution specified by f. So that's how the method works. Let's do a quick example. So suppose we have the exponential distribution. So this distribution has a parameter theta, and this is the CDF, 1 minus e to the negative x over theta. First thing we do is compute f inverse. So if we say u equals 1 minus e to the negative x over theta, we want to solve for x. So we have e to the minus x over theta equals 1 minus u. Take natural logs of both sides. On the left, the natural log will undo the exponential, but we can write it for now. ln of e to the minus x over theta is natural log 1 minus u. Again, the natural log and the exponential undo one another, and we have negative x over theta is natural log of 1 minus u, or x equals negative theta times natural log of 1 minus u. This now gives us the inverse function of f. So we have f inverse of u is negative theta natural log quantity 1 minus u. We then notice, just to make this a little simpler, the way you would actually use this method for this particular example is that if u is uniform 0, 1, then so is 1 minus u. And that's a quick exercise to check. But that means, why use 1 minus u here? We can use just u. So for the inverse transform method for the exponential, we use y equals negative theta natural log u. One might say, why bother making that change? Well, think about the situation where you might be doing a Monte Carlo routine and you might be generating millions of samples of a particular random variable using this method. Well, that extra subtraction happens a million times. It happens once for each one of your samples. So if you can eliminate that operation, you make your algorithm leaner, quicker, more efficient. But this is one example where we see that if you have a uniform 0, 1 u, setting y equal to negative theta times natural log of u will impose that exponential distribution upon y. So there are many different examples we could do, and there are many different contexts where this comes up, but this is a very elegant, nice, and useful method for generating samples from random variables, or just generating random variables from uniforms when you have that nice cumulative distribution function.